Hi guys, today we're going to learn about piecewise functions. And basically what piecewise functions are is they're functions that are made up of different types of functions or different pieces of different types of functions. So for example, you could have something where you have a linear function that turns into a parabola, which then turns into another linear function. So this would be considered a piecewise function because it's made up of three different parts. And in order to come up with an equation for this, you would have to use your linear function, so y equals mx plus b, as well as your parabola, or your quadratic functions with x squared in there. And the piecewise function really depends on what are the x values to be able to say, okay, well that portion of the function is a line, or that portion of the function is a parabola. So you're going to see these restrictions, what we're going to call domain restrictions, when we go to graph these. So let's look at this first opening exercise here. So it wants us to sketch the graph of these two parts. And in the end, we're going to end up coming up with what's called a piecewise function. So the first part is going to be this equation here. And remember, this f with a little subscript 1 just means, okay, well, that's the first part, and then f2, that's the second part that we're going to look at. This is essentially the same thing as saying y equals x squared plus 1. The important part of this, though, is what we're going to call our constraint, or our domain restriction. And that means we're only going to graph this part of the function when x is less than 0. We do want to include all the way up to the point when x equals 0, but we're going to use an open circle at that point because we don't want to include x equals 0. We just want all of the decimals and all of the numbers up to 0. So when we go to do this, we're going to start at 0, but I'm going to use an open circle at 0 because, again, it's not equal to 0, so that tells me use an open circle. And then we want to include all of the numbers less than 0, so -1, -2, -3, and so on. And the whole reason why you might be thinking, well, why can't we just stop at -1 if it says x is less than 0? Well, what about all of the negative decimals between 0 and -1? So that's why we go to 0, but we use an open circle because that's just working as like a boundary point. So now what we're going to do to get our y values is two ways. You can plug this into your graphing portion of the calculator. Go to Control-T to get to the table and just fill in some points, or just simply plug in 0 for x. So 0 squared plus 1 will give me 1. Then we can plug in -1 squared, so -1 squared becomes 1, plus 1 gives me 2. -2 squared becomes 4, plus 1 gives me 5. -3 squared gives me 9, plus 1 gives me 10. So I'm going to go ahead, I'm going to plot these points. So 0, 1, notice it's going to be an open circle. Then I have -1, 2, -2, 5, -3, 10. And remember, this has an x squared in it, so I know that it should look like part of a parabola, which it does. It looks like the left-hand side of a parabola. And the left-hand side is going to have an arrow on it because I want all of the numbers when x is less than 0. So yes, I would want to plot points at -100. So I draw the arrow representing that this graph continues to the left. At this point, when x equals 0, I have an open circle because that's working as a boundary point. I want to include all of these negative decimals here. So when x equals -0.5, I do want a y value there. So that's why I have to have an open circle at whatever this number here is. And notice that the graph won't continue to the right because I only wanted to graph the portion when x is less than 0. So then the next part of this graph, so here's again y equals x minus 1, this is going to be a linear looking graph. The reason why I know it's linear or looks like a line is because it's just an x, where this one was quadratic because it had the x squared in it. So it looked like a parabola. So for this one, we're going to use this equation and we're going to use our domain restriction. Now again, you're going to start at 0 because that's going to work as your boundary. But this time at 0, you can include 0 because it's saying x is greater than or equal to 0. So you're going to have a solid circle or a filled in circle at 0. So that means I'm going to just put a little, I like to just mark an open circle or a solid circle at those points so you remember when you go to plot it if it should be open or solid. So then I want numbers that are bigger than or equal to 0. So 1, 2, 3. You could keep going, but that's enough. And then you're going to plug them in or use your calculator to complete the table. So 0 minus 1, negative 1. 1 minus 1 gives me 0. 2 minus 1 gives me 1. 3 minus 1 gives me 2. Go ahead and plot these. Remember, it should look like a line. So 0, negative 1 is filled in. Then we have 1, 0. Then we have 2, 1. 3, 2. And it would just keep on going. And it's only going to keep on going to the right. So when I go to connect this, remember, you only want your arrow going to the right because you want when x is greater than or equal to 0, greater than 0 would be on the right-hand side. I don't want anything less than 0. So that's the important part of this. So this is what we call a piecewise function because it's part of a parabola, part of a line. Now the piecewise function that I drew up here, I connected them, so that just means this is continuous because I can just trace the whole thing. This would be a discontinuous piecewise function, or what they call a jump piecewise function, because it jumps from the parabola to then get to the line. But it's still a piecewise function. So it still is a function too, because this is an open circle, this is a closed circle. So if I were to draw a vertical line through there, it still passes a vertical line test because really it's technically only passing through one point. This is the only point at x equals 0, as would be x equals 0 would be y equals negative 1. This is just an open circle serving as a boundary of where the parabola stops, is basically what it's doing. So that's why we can still call it a function. So the notation for this piecewise function, if you look here, basically this was the first equation, the x squared plus 1, and then it has comma x is less than 1. So it means graph x squared plus 1 when x is less than 0. And then the second equation, graph x minus 1 when x is greater than or equal to 0. So this is the kind of notation that you guys are going to end up seeing. It's just you're going to have to know that this means break this up into two parts. Break it up into the first part, which was what we did here, y equals x squared plus 1. Then break it up into the second equation, x minus 1, and graph them based on these domain restrictions. And that's your piecewise function. Now, when it comes to evaluating these, which is the next part, meaning f of negative 4, remember this means that negative 4 is the input. You want to find the output. Well, when it's a piecewise function, you're going to have to look at, well, where does negative 4 fall? Does it fall in the first equation or into the second equation? So if I'm looking at negative 4, is it less than 0 or is it greater than 0? And the answer is it's less than 0. So since negative 4 is less than 0, you're going to use the first equation to plug into, which means I'm going to take negative 4 and I'm going to plug it in to this, I'm going to call it number 1 and number 2, into the first equation. So x squared plus 1, so I put parentheses where the x was, so we get 16 plus 1, so you get 17. So it's just like evaluating functions before. The only difference is you have to decide, since there's multiple parts, you have to decide, well, where does this input fall? Under which domain does it fall within? So for this one, your input is 0. Ask yourself, well, where does it fall? Does it fall into equation 1 or equation 2? And in this case, it's 0. So equals 0 is in equation 2. So 0 equals 0. So use equation number 2. So when you plug in, you get 0 minus 1 gives you negative 1. And then the last one, 4, is greater than 0. So you're going to use the second equation. So parentheses where there's an x, minus 1, plug in your 4. 4 minus 1 gives me 3. And that's it. Now, for these, I just basically showed you without using the graph, because there's going to be times where you're just going to be given the equation and you're just trying to evaluate, so you don't necessarily have to graph. But if you already have the graph done, I think it's almost easier to look at the graph. So let's just look at these really quick on the graph as well. So if I was trying to evaluate negative 4, I could go over to the graph and then I would easily see that I'm trying to use the parabola part. So in this case, -4 isn't a point I plotted, so I would still want to plug it into the equation, but it's easier to see that I definitely want to use the parabola equation because -4 would fall in the green section of the graph. Then if you move to 0, well, 0 you'd have to use a solid circle, so -1, because this open circle is only a boundary. It's not really a point on the graph. And then 4, when x equals 4, you go up and you see, okay, well, that's at 3. That one's easy to see. So you can still use the graph to evaluate, but you won't always have the graph drawn. So it's good to know how to do this algebraically. And it's the same thing that we've been doing. You just have to think about first, well, what part of the function do I plug into before you plug in? So let's do more practice with this so you really get the hang of what a piecewise function is. So let's try another example. So this example, it has 3 different parts to it, so 3 different pieces, which really isn't a big deal. It's the same process, you just have 3 separate parts. So when you go to do this, number your equations, or number the different parts. You have 1, 2, and 3. So for the first one, I have y equals x plus 1, and I'm going to go ahead and I'm going to set up a table for this. So remember, this is your restriction right here. So that tells you when to use x plus 1. So x is less than 0. So I'm using this equation, y equals x plus 1, whenever x is less than 0. So we're going to start our table at 0. And you have to ask yourself, is it going to be an open or closed circle? It's going to be open because it doesn't have the equals bar. So it's going to be an open circle at 0. And x is less than 1. So ask yourself, well, x is less than 0. Ask yourself, what kind of numbers are those? Well, x is less than 0 would be all of the negative numbers. So we have -1, -2, -3, and so on. So now plug these into your equation. So 0 plus 1 is 1. -1 plus 1 is 0. -2 plus 1, -1. -3 plus 1, -2. So go ahead and plot those. So 0, 1, it's going to be an open circle. -1, 0, solid. -2, -1. -3, -2. You could plot more points, but at this point you should know that it's going to keep on going to the left, your graph. So I'm going to go ahead and I'm going to connect going to the left with an arrow. And that's the first part. So then we move on to the second part. And remember, you have an arrow going to the left because you want to include when x is less than 0, so all those negative numbers, but we don't want anything going to the right. So then the second graph, y equals 1. It's just 1 here. Here's my restriction this time. So when I go to do my table, it's going to start at 0, and it's going to end at 2 this time. And I'm going to have solid circles at both of those points. And then include any points between these. So 1 is the only point. So x has to be, when x is between 0 and 2, the y value is 1, is what it's saying. So when x equals 0, y equals 1. When x equals 1, y equals 1. When x equals 2, y still equals 1. So now we graph those. So we have 0, 1. So now this becomes filled in because it's a solid circle there. We have 1, 1, 2, 1. And this is just going to be a horizontal line. So I connected those. Now I move on to the third part, which is y equals -x plus 3. And this one, your restriction is saying x is greater than 2. So I'm going to start at 2. It's going to be an open circle. And when x is greater than 2, so numbers bigger than 2, so we have 3, 4, 5, and so on. So my arrow is going to keep on going to the right this time. Where this one, my arrow kept going to the left because it was negatives. So plug in 2, so it's going to be -2 plus 3 is going to give me 1. -3 plus 3 is going to give me 0. -4 plus 3 is -1. -5 plus 3, -2. Go ahead and plot them. So 2, 1 is an open circle, but since it's already been filled in by the green portion, it's really still just going to be a filled in circle there. Then we have 3, 0, 4, -1, 5, -2, and then I'm going to just go ahead and connect those. And remember, I'm going to have an arrow that goes to the right. I want to include all of the values when x is greater than 2. So there's my function. So we can just label that entire graph g of x. You don't need to worry about labeling each part because this entire function is called g of x, the 3 parts put together. So now let's look at evaluating. So for this portion here, g of 4. So g of 4, there's a couple ways you can do it. You can go to when x equals 4, which is right here. What's the y value? Well, the y value's at -1. So -1. You could have also said, okay, 4, where does that go? 4 goes into this third equation. So if you use number 3, that means I would take negative, plug in the 4, plus 3, which equals -1. So this is using the graph, using the equation. 1.5. So if you go to 1.5 on the graph, you go up, you see that it equals 1. If you go to 1.5 using the equation, well, 1.5 is in the second part here. So if it's in the second part, you're going to use number 2. If you plug in 1.5 into 1, there's no x here, it's just going to equal 1. So it would just equal 1 if you were using the equation, because there's nothing to plug 1.5 into. -6. So -6, I don't have an exact point plotted, but if I continued with the slope here of this line, I would see that this point is at -6. The y value is -5. But again, look at where -6 falls. It falls in the first equation. You can use 1, equation number 1. So if you plug in -6 in for x plus 1, you get -5. So you get the same answer. And then for 0, 0 is one of those boundary points. So you have to look at, well, which one does it belong to? 0 belongs to equation number 2, or part 2 of this. So you can look at the graph. If you look at 0, it's going to be 1, the y value. Or you can say, well, if I'm going to look at my equations here, I would use equation number 2 because that's when we equal 0. So if you use number 2, it's just going to equal 1 because, again, there's nothing to plug into. So then the next part of this is just looking at where is it increasing, decreasing, and constant. So for this, increasing, decreasing, and constant, I see that this graph is doing a little bit of everything. If you look at it from the left to the right, it goes uphill, and then it remains the same, and then it goes downhill. So the red portion is increasing, then it remains constant, and then the blue portion is decreasing. So over the 3 parts is where it changes. Now, just because that happened to be the 3 pieces are where increasing, decreasing, and constant change, that's just a coincidence here. It doesn't always happen where the pieces change. So you could have a situation where you have an increasing parabola that turns into a line, it's still increasing. So don't worry, don't think that it's because that's where the graph was broken up. It's just coincidence. So let's actually state the intervals. So increasing, I see in the red section here. So from -infinity, remember we read the x-axis. So -infinity up to 0 is where it's increasing, is where it's red, is where it's going uphill. So from -infinity to 0, we use round brackets for these because increasing, increasing, decreasing, constant, you always want to use round brackets. We see that it's constant in the green section. So it's going at a flat rate here. So from 0 to 2, the x values are 0 to 2 is where it's constant. And then the portion of the graph that's decreasing is going to be from 2 to infinity. So remember, you're reading off the x-axis. So it starts decreasing at 2 and keeps on decreasing to positive infinity when x equals positive infinity. So decreasing from 2 to positive infinity. And then down at the bottom here, I just want to summarize the procedures that we basically just went through. So the first thing when you go to graph these piecewise functions is that you want to graph each piece of the function separately over each domain restriction. So you break it up into however many parts are given to you. So that's the first part. So go ahead and write these steps down so that you have them as the procedure when you have to do this on your own. So there's your first part. The second part to this is you have to decide what kind of symbol to use or what kind of circle to use. Is it going to be an open point or a closed point? So if you have the less than or greater than symbol, you're going to use an open point. If you have less than or equal to or greater than or equal to symbol, you're going to use a solid point. So that's always going to be when whenever you're graphing those constraint boundary values. So what I mean by that is when it says x is less than 0, so at 0, you're going to use an open circle. If it says x is greater than or equal to 2, at 2 means you're looking at a solid circle. So it just depends on whatever that number is in the inequality. That's what I mean when I say the constraint boundary value. And then the last piece here is going to be that you always want to graph those constraint boundary values of the domain. So I'm going to just add an example here of what I mean when I say these values. So for example, I have f of x equals x plus 1, comma, x is less than 2, and then I have x, comma, when x is greater than or equal to 2. 2 is going to be my boundary value. So that's where the graph is changing. So it's where the pieces are now different. So these are what I'm calling the boundary values. So overall, the general process is you have to graph your separate parts, and then you look at these constraints, these domain restrictions, and you look at those boundary values as open or closed circles. And that's how you generate your table of values to plot, is based on those values and based on your restrictions. So if you need more time to copy this down, just pause the video, and then when you're ready, I have a couple more examples that I want to do with you before you go. So on the next page, we have a couple more exercises here just to graph and look at, just more practice. So for this first exercise, we have 2 parts to look at. And with these 2 parts, we have our domain restrictions. So let's get our 2 situations here. So our first one is going to be y equals x squared minus 1. And when x is less than 0, so when I go to write my table, I'm going to start at 0, and I know it's going to be an open circle, and it's when x is less than 0, so the negative values. And then we're going to plug these in. So 0 squared is 0, minus 1, negative 1. Negative 1 squared is 1, minus 1 is 0. Negative 2 squared is 4, minus 1 gives me 3. Negative 3 squared is going to be 9, minus 1 will give me 8. So go ahead and plot these. So 0, negative 1 is an open circle. Negative 1, 0. Negative 2, 3. And negative 3, 8. And remember, we saw an x squared, so we should be thinking that this looks like a parabola, which it does. And I have an arrow going to the left because I want when x is less than 0. So I want to include values on the left-hand side. And then for this number 2, we have y equals x minus 1. We're starting at 0 again. That's our boundary value. We're going to use a solid circle because x can be greater than or equal to 0. So then I want numbers greater than 0, and we plug them in. So 0 minus 1 is negative 1. 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. Go ahead and plot those. 0, negative 1 is the same point, so now this becomes filled in since it was a solid circle. 1, 0, 2, 1, 3, 2. And I know that this is going to be a line because it was just an x minus 1. So I'm going to go ahead and continue my line. And I make sure I put an arrow to the right on that because of the fact that I want x being greater than 0. So I want to include all of those positive values. So there's my function. I can label it f of x, partially a parabola and part a line. So there's a piecewise function. This is continuous because there's no break in the graph. It just keeps on going. So now let's look at evaluating it. So f of -4, well, -4, you decide, well, which category does -4 belong to? It belongs to equation number 1. So you would use equation number 1. -4 is less than 0. So if you plug in -4, you would get 16 minus 1, so you get 15. You could also look on your graph, but the problem is -4 isn't part of the graph, so you won't see that, so you still have to plug it in, but you definitely know that it does belong to the second, or the first equation here, the parabola part of it. Then I look at 0. 0 is going to belong to the second equation, so I could plug that in, and we get -1. Then I look at 4. 4 belongs to the second equation as well, because 4 is greater than 0. So this is going to be the second equation, so we're going to plug that in. 4 minus 1 gives me 3. Again, 0 and 4, you could have just easily looked on the graph. 0 is at -1, 4 is up here at 3. Or you could at least see from the graph, okay, it belongs to the line, so plug it into the line equation, or the linear equation. Alright, and then the last thing here is going to be, I want you guys, before you leave, so let's skip this example, or exercise 2, and let's have you guys do the exit ticket. So you should have about 10 minutes left in class. So based on what we just did together, look at the last page in the notes. I believe there's a summary page in your notes, so you can read through that if you want. But really what I want you to do is that very last page, detach that and write your name on it. It should be the exit ticket, and I want you to use your notes and do what you can so that I can see what you've learned from the video when I come back. So go ahead and do that and turn that in before you leave class, and then you guys have a worksheet for homework that's more practice with this. Alright, well, have a great rest of your day, guys.